Shout out, Popio. Shout out. Hope you're watching. Probably not. All right. All right, here we go. So, here's where we were yesterday. Again, remember that we really have not learned anything new in this section, right? There's really no new material. It's just kind of like a compilation of everything that we know about graphing. Just as a reminder, we've got these guidelines, and in the homework problems, it will say, use the guidelines to find, to graph all of these things, right? Okay, we got domain, intercept, symmetry, and then all the calculus stuff. Intervals of increase, decrease, maximum, minimum, concavity, and then sketch. We good? We good over there? No. All right. So we were here. We had all of this information, right? We got everything that we need here. We got the domain, everything but -1, +1. We found the y-intercept, which is also conveniently the x-intercept at 0, 0. We know that it's even, which means it's symmetrical about the y-axis. We know that there's a horizontal asymptote at 2. There's 2 vertical asymptotes at 1 and -1. That the critical point were -1 and +1. Oh, wait, they didn't exist. But then again, at 0, so there's a maximum value at 0, 0. We know it's always increasing from -infinity to 0. It's always decreasing from 0 to infinity. And then we did that long process of finding f double prime just to find out that we have plus or minus 1 that's not part of our domain anyway. That could have been the inflection point. So we know that there are no inflection points. So now we graph. Okay, now we graph. Now, it kind of is up to a problem by problem basis on where you start your graph. Here's what I will say about this particular problem. Okay. In terms of this one here, I know there's kind of some like boundary lines. What are the boundary lines that we have? The asymptotes. We know that there's a horizontal asymptote at 2 and 2 vertical asymptotes at 1 and -1. So I'm going to say this. Here is +1, here is -1, and here, that's pretty off center, that's okay. And here is +2, all right? And I might want to go up a little further past that too. Okay. Okay, so -1, +1, and was it +2 or -2 for the horizontal? +2 for the horizontal. Okay. Now, from here, I have to then take and see, okay, where are my critical values? Well, I know it's got a maximum point at 0, 0. Right? It's got a maximum. So it's going to stay below that. What does it mean for a vertical asymptote? It means it's going to dive down or dive up. Is it going to dive up? No, it's a maximum. So I know that this is the case. And if this is symmetrical about the y-axis, then I know this has to look identical. Now, what to do on the left and right side of this vertical asymptote? Well, I have to say this. It's going to go to 2 on either side, right? It's going to go to 2 on either side. And it's always going to be increasing. It's always going to be increasing, right? It's increasing from -infinity all the way to 0, which makes sense because from -1 to 0, it's increasing, right? It's also got to increase here. So there's really 2 options on the left side of -1. It could look like this. But is that increasing? No, that's decreasing, right? So it can't look like this. The other option would be like that. Is that increasing? Yes. Okay, whatever it looks like on the left side, it's got to look like on the right side. So there. And there's our graph. Should have made it smaller. Okay. questions about that. So again, use your guidelines of your horizontal and vertical asymptotes, if they have them, to kind of inform what you want it to look like. It's a pretty big process. I know. I agree with that. But too bad. So sad. All right. Okay, so the new thing I want to talk about is slant asymptotes. Now, correct me if I'm wrong. I do believe you guys have studied slant asymptotes before in pre-calculus. You might have called them oblique asymptotes, maybe. I don't know. But you probably didn't talk about them very much. The only really asymptotes that we work with very often are horizontal and vertical asymptotes. But there are such thing as slant asymptotes. Like, for example, if you've got some function that looks like this, and it's gonna, I don't know, go like whoop, and then maybe do like a whoop, right? I don't know what happens on the end there. I'm just gonna put arrows. But do you see? Don't make fun of my sound effect.
It's a new one.
I know. But do you see the asymptote running through there?
Yeah.
So we have to learn how these come into play and what the equations of those things are, because it's really easy to identify the equation of a horizontal or vertical asymptote, right? It's just x equals or y equals that number. But for this, I mean, that's going to have a slope. Like, that's going to have a slope. It's going to have a y-intercept. So how do we actually calculate that? So here's what we do. Some curves have asymptotes that are oblique or slant asymptotes. That is neither horizontal nor vertical. So basically saying this, the limit as x goes to infinity, as I make x get really, really, really big, that the function and some line, mx plus b, the function of some and some line, the difference in between the two is going to become negligible. Right? If I keep going out further and further and further to infinity, won't this line and this dotted line, this blue line and the dotted line start to look exactly the same? If I stretch it out to infinity, if I make it really, really big, that line and the blue line, the asymptote and the line, are going to look identical. So that's what we're saying here. The limit as x goes to infinity of f of x minus mx plus b, the function and the difference between the function and the asymptote is going to be negligible. It's going to be 0. Okay? So that's basically the definition of a slant asymptote. Now, how do you find it? Now, for rational functions, slant asymptotes occur when the degree of the numerator is 1 more than the degree of the denominator. That's the rule. Okay? That's the rule. For rational functions, the slant asymptote can occur, and this is the only time it can occur. The slant asymptotes occur when the degree of the numerator is 1 more than the degree of the denominator. That's how you know it's going to happen or could happen. Okay? When the degree of the numerator is 1 more than the degree of the denominator. So it's top heavy, which means there is no horizontal asymptote, which makes sense. There is no horizontal asymptote, but there could be a slant asymptote as long as the degree of the numerator is just 1 more than the degree of the denominator. So like x squared over x. Well, that wouldn't work because that would have a hole in it instead. But you get the idea. If you have something with a numerator having a degree of 3, then the denominator would have to have the degree of 2. Now, in such case, the equation of the slant asymptote can be found by long division. Long division. That's how we find it. I know, it seems weird, but we actually have to take long division of polynomials to find what the slant asymptote actually comes out to be. So, throwback time. Let's do some long division. X to the third over x squared plus 1.
I was advanced. You didn't even know what. No, I was advanced. You don't get it. I was above everybody else.
Okay, so this is what we're going to do. We're going to take x squared plus Now, I like to leave all terms represented. 0x plus 1. And we're going to divide that into x to the third. And I like to leave every term represented. Plus 0x squared plus 0x plus 0. I know, I'm weird like that. If you had Mrs. Apples or Mr. Grubb, you might not have done it. If you had me, I definitely did this. I put 0 in as placeholders for everything. Now, remember what long division does. This is kind of like almost too simple of an example. I do have another example that we will go through that kind of shows it a little bit more in depth. This is almost too simple of an example. So remember how we do long division. We say, how do I make my first term look like my first term over here? What do I multiply x squared by to make it look like x to the third? X. So I like to put it right on top of that term. And now I distribute in. So this is x to the third plus 0x squared plus 1x. Right? I take the number on the top times the number outside, and I bring it down. And now we subtract. Okay, so we take x to the third minus x to the third, that goes away. X squared minus x squared, that goes away. So that's going to be a 0x squared. I know I'm weird. I like to keep that as a 0x squared. And a 0 minus 1 is minus 1x. Carry down our... No, that's just a 0. My wife teaches this in 6th grade, and she has the... I can't remember exactly what it means, but she has the acronym that says, does McDonald's sell cheeseburgers? Does McDonald's sell cheeseburgers? Now this is just for numbers, but she says divide to figure out what you need to multiply by. Divide to get that number. Multiply to get to this. Subtract. Carry down. Does McDonald's sell cheeseburgers? I think that's what it means. Okay, so now we say, how do I make x squared look like 0x squared? Multiply by 0, right? No, that's an eraser. So this would be 0x squared minus or plus 0x plus 0. And that gets us a, and now we subtract down, negative 1x plus 0. And I'm done carrying down now. So minus 1x is my remainder. And you know it's a remainder because now the degree here is less than the degree here, right? The degree down below is less than the degree here. So that is truly a remainder. So what did I divide here? This actually comes out to be an x plus, minus x over x squared plus 1, right? That's what it comes out to be. You take the remainder over what you were dividing by. X over x squared plus 1. And I just made it a minus because it was a negative 1x. Okay, now let me ask you something. This is the division with remainder x, with the remainder x, negative x over x squared plus 1. We just got done saying that in the long run, as I make x go to infinity, the difference is going to be going to 0. So we're not looking at this in the short term. We're looking at this in the long term. What happens as I make x go to infinity? What happens, and more specifically, what happens to this as I make x go to infinity? It goes to 0. Why does it go to 0? Because it's going to make the denominator bigger and bigger and bigger and bigger than the numerator, right? Obviously, this is going to go to infinity, but this is going to go to infinity faster, right? Because it's x squared. So this is going to go to 0. This is going to be negligible in the long run. So what does that mean? That means the equation is, of the slant asymptote, y equals x. That's the slant asymptote, y equals x. So when I graph this, and I will do this in a second, when I graph this, I should see a diagonal line, y equals x, running through this graph as a slant asymptote. So basically what you could do is long divide and then just like throw away your remainder. You don't pay attention to your remainder. The remainder just goes away. Why does it go away, though? That's important to understand. It goes away because we're looking at the long term. Now, I'm going to use Desmos to graph this. So I'm going to say, we got, what is it, x squared, x cubed over x squared plus 1. Oh, not that. X cubed over x squared plus 1. X cubed divided by, no, x cubed. Okay. Divided by, or whatever, x squared plus 1 or minus 1? Plus 1? And let's also put in the line y equals x. Okay, so do you see in the long run, it's getting closer and closer. And in the long run, the difference is negligible. The difference is ending up to being 0. We see that? That's the idea of a slant asymptote. So you can always go ahead and check back your answer. Now the only problem is, do you have Desmos or your calculator on this portion? No. So you gotta kind of trust yourself. But if you're working on your homework and you really want to check, okay, is that the correct slant asymptote? Throw it in Desmos and see what happens. Okay. Let's do another one of those, shall we? I've got this problem. This is actually 62 from your homework. Problem 62 from your homework. 4x cubed minus 10x squared minus 11x plus 1 over x squared minus 3x. And I think like 61, 62, 66, I think they just say, find the slant asymptote. Those aren't graphing ones, I don't think, if I remember correctly. Just find the slant asymptote. Do you guys remember doing this in pre-cal? No. When I asked him about it, I think I asked him about it last year, and he said, "Yeah, we talked about it for like a day, maybe like a lesson somewhere in there, but it's not much." Maybe not. No, I don't know. All right, so we now could a slant asymptote occur? Yes. Look at the degree on the top. It is 3.
Wait. Oh, I wrote it wrong. That's tough.
Yeah. You know what I could do to make a slant asymptote not occur? Just make that like 4x to the 4th on top. Then there's no asymptotes. No horizontal, no vertical. Well, I guess vertical we'd have to check. There might be vertical, but there would be no horizontal, but there would definitely be no slant asymptotes. Because I would have made the degree on the numerator 1 bigger. Yeah. So it's gotta be a difference of only 1 degree. X to the 3rd on top, x squared on top, x squared on bottom. If I would have made that x to the 4th on top, no more slant asymptote possibility. Okay, so we take x squared minus 3x, and again, I like to put in a plus 0 here, divided by, and all terms need to be represented, 4x to the 3rd minus 10x squared minus 11x plus 1. Good. All terms are represented. Okay, so how do I make x squared look like 4x to the 3rd? What do I multiply by? 4x. Just 4x. So I take 4x times x squared to make it 4x cubed. I take 4x times negative 3x to make it minus 12x squared. I take 4x times 0 to make it 0x. We subtract. I always like to remind myself to subtract by using parentheses like that. That's just a visual reminder that, yeah, you do have to distribute that negative. Okay, bring it down. That cancels successfully. That's what we wanted to happen. Negative 10x squared minus a negative 12. So negative 10 plus 12 is a positive 2x squared. Negative 11 minus nothing is negative 11. Carry down. Now I keep going. How do I make x squared look like 2x squared? Multiply by 2. 2 times x squared is a 2x squared. 2 times negative 3 is a negative 6x. 2 times 0 is 0. Oops, that's not a plus, that's a minus sign. And now we subtract down. 2x squared minus 2x squared cancels. Negative 11x minus a negative 6. Now be careful, you're negative 11 minus a negative. That's a plus again. Negative 11 plus 6 is a minus 5x, and then plus 1. Now I know I can stop because the degree of the remainder is now smaller than the degree of the denominator, right? This x is now smaller degree than what I was dividing by. So I know that this is truly 4x plus 2 with the remainder of negative 5 plus a negative 5x plus 1 over x squared minus 3x. Now, that's the formal way to write what it would look like if you divide. But do I even need to worry about my negative 5x plus 1 over x squared minus 3x? No. Because of the remainder being 1 degree smaller than the denominator now, this ensures the fact that if I stretch this to infinity, that will be negligible. This whole thing goes to 0, right? Because the denominator is bigger than the numerator, it will end up being smaller number on top than on bottom. So it's going to go to 0. So I know the equation of the slant asymptote is y is equal to 4x plus 2. Let's go to my graph to confirm it. Now, I did not graph this one ahead of time, so I have no idea what this is going to look like. That's okay. Leave Desmos.
Like when it goes to infinity. I think so because that is the definition of
This is going 0.
4x. Do that third.
No.
Minus 10 squared
Yeah, because
minus 11.
as it goes to infinity, it is 0. Yeah.
X squared minus 3x.
What? What are you saying? What are you saying? Go.
And let's plug in our 4x plus 2. Now, look at what's happening on either side. It's going through this piece of the function, but there must be some weird stuff happening in the middle because I really only care about what's happening on the ends. Look down here. You see how it's getting closer and closer down here? Let's check the opposite side. What the heck are you doing? Yeah, it's going to go through but look on the far right. On the far right here, it's going to keep getting closer and closer to my asymptote. Yeah, we're at almost at 70 in the y values. Yeah, up to 80. So again, it can cross through the middle. The only thing you care about is what's happening on the ends. It's the only thing you really care about. Because that's really what the definition of a slant asymptote is. As x goes to infinity. Or negative infinity, right? As x keeps getting smaller and smaller or bigger and bigger. It should happen in both the same, opposite directions on either side. Okay? Questions about that? No? I am just going to let you guys work on the homework now. Because this is there's a lot of graphs on here. And you know what? I could show you another example, but we've graphed a lot. So I think it's now time to just let you graph. Let you try them out, and we'll work on those problems. Does that sound good?
How many of those ones are we doing
All
big
of them.
problems for?
All
Or
of them.
all the
You
big
do all the
problems?
ones that are on the board.
Are they all
You do all those ones.
Max, no exceptions.
No, I know that. I'm